Now you see, let's say if we want to, so this is for the semi-linear case, right? If we want to do similar sort of thing in a quasi-linear case, what do we have? So in the quasi-linear case, the equation which we are essentially talking about is looks like this: a of xy, and then let's say u, and u of x, right? Plus b of xy, u of y. This is equals to c of xy u. You remember this is a quasi-linear equation, right? So let's call this a quasi-linear equation, QL. Okay, and what is your Cauchy data? So what is your Cauchy data in this case? The Cauchy data is given by this. So this is your gamma, gamma. So you see, u restricted to gamma is, let's say, given to be phi. Okay, where gamma, this is a curve, right, gamma, and that will be given as, so basically gamma of phi is given as gamma 1 of r, gamma 2 of r, and phi of r. Okay, so phi of gamma 1 and gamma 2 basically, yes. So we can just write it like this, but let's just stick with phi of r for now. Yeah, so this r is in r or some interval in I, interval which is in r. So basically let's just call it as a r. Okay, the parameterization. Okay, so the thing is this, we want to write down this particular star, but in this case, okay, so star in this case will look like this. See, essentially we'll write this. Okay, so let me do it this way. It will look like this: a of gamma 1 of r, gamma 2 of r, and then I have another, this u part is there, right? Yes, and this u part we have this extra this phi, right? Okay, so in this case you will have phi of r, and then so this is one case, one second, yes, and where am I? Yeah. And similarly b of gamma 1 of r, gamma 2 of r, and phi of r. Yeah, okay, and this dot with minus gamma 2 prime of r and gamma 1 prime of r. Okay, this should be non-zero. So essentially a similar sort of thing. This is for the quasi-linear case I am writing. So q star q. So this is basically the non-characteristic condition. Okay, so gamma is called a non-characteristic if this happens. Okay, and this condition, this particular condition is called the transversibility condition. Transversibility condition. Okay, the curve is called the non-characteristic if transversibility condition holds. I hope this is clear. Okay, so now let's just write down what is the existence and uniqueness theorem. Right, so existence and uniqueness, and please remember this is local uniqueness, and I will do it for a quasi-linear case. So basically even semi-linear case is actually considered there. Okay, so first of all, let omega subset of R3. So I am starting with a domain in subset of R3 is an domain. So basically your domain means open and connected sets. Connected set. This is what I am starting with, and I am also starting with some coefficients a, b, c, which is basically c1 of omega. C1 of omega means they are continuously differentiable in omega. Yes. Okay. Now consider this QL equation along with, so basically this along with these two conditions, the initial data along with this condition. So consider QL, consider the problem, the quasi-linear problem, QL. Let me write it down again for better understanding. A of xy u, u of x plus b of xy u, u of y equals to c of xy u. Okay, and the data is given by, let's say, let me write it like this. So xy z, and the data is given by gamma 1 of r. Maybe I can just write it like this. So you see, so basically gamma and phi, this is your initial data, right? So it is given by x is nothing but some f of s, let's say. Y is nothing but g of s, and z is nothing but h of s. Z is basically u, and this s is in some interval I. Yes, and what are f, g, h? F, g, h, these are nothing but continuously differentiable function on I, such that f prime s, the square of that, plus g prime s, the square of that, has to be non-zero, okay, for all s in I. So basically what does that guarantee? It guarantees that this is a regular curve, okay, such that this gamma, the curve gamma and phi, gamma and h, let me write it like this, gamma and h. So gamma and h, this curve should be in omega. Is it okay? Right. Now we have to have another condition. What is the condition? Moreover, the transversability condition should hold. Moreover, okay, let's say p naught of x naught, y naught, z naught, which is given by f of s naught, g of s naught, and h of s naught. Okay, and this belongs to that curve gamma. Okay, gamma and h. Okay, so this belongs to that curve where s naught is in I. You can write s naught, you can write s r naught. It's basically a parameter which I'm writing it like this. Okay, so assume the transversability condition now. Assume that this condition holds, that a of f of s naught. Okay, so I am changing the notation a little bit. Here I used gamma 1, gamma 2 and phi. Here I am using f, g and h. So just a notation change, nothing special. I'm just changing the names. So this is g of s naught and h of s naught, okay, times g prime of s naught. Okay, so you see this times this essentially, and this times this. So basically this condition I'm writing it like this. Okay, minus b of f s naught, g of s naught, h of s naught. Okay, dot f prime s naught. So this has to be non-zero. Is it okay? Then the conclusion says that the Cauchy problem, then the problem, which problem? The problem which we are studying here, let's call it the Cauchy problem, okay, CP. Then the problem CP, okay, has a solution, okay, which is defined on a neighborhood, NBD. This is a neighborhood, okay, of x naught, y naught, which is a part of the initial data gamma. Is it okay? So basically what it is saying is this, that if the transversability condition holds, that's the idea. You are looking for a Cauchy problem, quasi-linear Cauchy problem basically, yes, with smooth coefficients, and if your initial data is regular, yes, the transversability condition, this is the transversability condition. If the transversability condition holds, then there is a guarantee that there is a solution, but it is not like a solution everywhere, but in a small neighborhood of x naught, y naught. So basically what I meant is, let's say that this is your initial curve gamma. So this is your two dimension, in two dimension this curve is there gamma. Okay, and let's say there is this point x naught, y naught. Okay, so what it is saying is this, you will have a small neighborhood around x naught, y naught, some small neighborhood around x naught, y naught, where there is a guarantee that for this neighborhood u of xy exists, and that solves the problem CP, in this neighborhood. You understand? So around x naught y naught there is a small enough neighborhood where all of this there is a solution which satisfies CP. That's what it is saying. This is existence and uniqueness theorem. So basically, let's say if I give you a problem and if I ask you whether the existence and uniqueness theorem holds or not, you just have to check the transversability condition and then you are done, more or less. Of course, given all these coefficients are smooth. Okay, so let's look at one problem and then we'll leave. See,